Show by using the principle of mathematical induction that for all n belonging to the set of natural numbers n, and for n values greater than or equals to 1, u of n equals 1 over square root of 5 multiplied by this particular expression. And it's given here that u1 equals to 1, u2 equals to 1, and u of n plus 2 is given by this relation u of n plus 1 plus un for n greater than or equals to 1. Okay, let us begin. So first, what we'll do, we're going to suppose a statement represented by P of n. So let P of n be the statement which is given by, we have P of n such that u of n equals 1 over square root of 5 multiplied to, we have 1 plus square root of 5 divided by 2 whole raised to the power of n, minus we have 1 minus square root of 5 whole divided by 2 raised to the power of n. Fine. This is given to us. This is the statement, and we're going to label this as statement number 1. So we have to verify that this is a true statement for all n belonging to the set of natural numbers and n greater than or equals to 1. Now, let's try to verify for n equals to 1. So for n equals to 1, we get the statement P of 1 such that we have u1. This is going to be equals to 1 over square root of 5. So this is going to get multiplied to 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2. This is going to now give us 1 over square root of 5. So we can take the difference of these two terms within the parentheses, and that's a very trivial calculation which is going to give us square root of 5. So square root of 5 gets factored out from the numerator and the denominator, leaving us with 1. So this is giving us u1 equals to 1. And since we're already being provided in the problem that u1 corresponds to 1, so this means this tells us that the statement P of 1, this is a true statement. This is a true statement. Fine. Similarly, we're going to verify for n equals to 2. So let's verify if the statement is true for n equals to 2 or not. For n equals to 2, we have P of 2 such that u2, this is going to be equals to 1 over square root of 5 multiplied to 1 plus square root of 5 whole divided by 2. And this is going to be raised to the power of 2 minus 1 minus square root of 5 over 2 whole raised to the power of 2. So this is going to be equals to 1 over square root of 5. Again, I'm leaving this as an exercise for you to try out. So simplification gives us square root of 5, which is going to give us 1. And this tells us, and since u2, it was given in the problem that u2 is also equals to 1, so our statement, this implies that the statement P of 2, this is true as well. Fine. So we have shown here that the statement P of 1 and P of 2 is true. Now, in order to show that the statement P of n is true, we'll have to consider some other natural numbers. So here, we're going to assume that let P of m, where m corresponds to some natural number greater than 1. So let P of m be a true statement. Now, what is P of m? We have to specify the statement P of m as well. P of m is, we simply take the original statement P of n, and wherever we see n, we're going to replace it with m. So that means we have 1 over um equals to 1 over square root of 5. This is going to get multiplied to 1 plus square root of 5 divided by 2 whole raised to the power of m minus 1 minus square root of 5 divided by 2 whole raised to the power of m. So this is going to be our statement P of m, and we are assuming this is a true statement. So let's name this as statement number 2. So P of n is our original statement when we have now considered P of m to be a true statement. And once we consider P of m to be a true statement, our next step will be to show that the statement P of m plus 1 this is true as well. This is also true. This is our goal. The problem wants us to verify that P of m plus 1 is a true statement as well. Now we'll have to first understand what is a P of m plus 1. The statement P of m plus 1, this is simply take the statement P of m, and wherever we have m, we're going to replace with m plus 1. So that means we have to show that u m plus 1, this is going to be equals to 1 over square root of 5 multiplied to 1 plus square root of 5 divided by 2 whole raised to the power of m plus 1 minus we have 1 minus square root of 5 divided by 2 whole raised to the power of m plus 1. So this is what we want to show. So let's call this statement number 3. Our goal is to verify statement number 3. Okay, let us begin. Now here we're going to use the condition that's given to us. So here it's given that u of n plus 2 equals to un plus 1 plus un. So this was originally given to us in the problem, but what we'll do, we're going to replace the index n with m, such that we have um plus 2 equals to um plus 1 plus plus um. Now, since we want to verify P of m plus 1, that means we need to we need u of m plus 1. So what we'll do, we're going to rearrange the terms to get um plus 1. So that's going to be equals to um plus 2 minus um. Fine. Now, this is the condition that we are going to use to verify P of m plus 1. Now, what we need is u of m plus 2 and um. Since we have already considered P of m to be a true statement, so from P of m, we can take the help of Pm to obtain u of m, and to get u of m plus 2, all we have to do is replace this m with m plus 2 as well as this power m with m plus 2 as well. So that means we are going to get, so now let's try to further simplify. So we have um plus 1, this is going to be equals to, now from each of the two terms, we're going to take 1 over square root of 5 as the common factor. Fine. Then what we'll do, we're going to take this term and this term, and we're going to combine them to get a single term. That means we have 1 plus square root of 5 divided by 2 raised to the power of m plus 2, and we have negative 1 plus square root of 5 divided by 2 raised to the power of m. So this is going to be one single term. So let's combine it, and then we have these two terms. So if we take negative as the common factor, now we're going to have 1 minus square root of 5 divided by 2 whole raised to the power of m plus 2 minus 1 minus square root of 5 divided by 2 whole raised to the power of m. Fine. We are now going to further simplify. So this is going to be equals to 1 over square root of 5. Now from these two terms, what we'll do, we are going to take 1 plus square root of 5 divided by 2 whole raised to the power of m as the common factor, such that, so from this term, so here we had m plus 2, we'll be now left with 1 plus square root of 5 divided by 2 whole squared minus 1. Fine. Minus, now from these two terms, we're going to take 1 minus square root of 5 divided by 2 whole raised to the power of m as the common factor, such that now we are left with 1 minus square root of 5 over 2 whole squared minus 1. Let's further simplify. So we have 1 over square root of 5. This is going to get multiplied to 1 plus square root of 5 divided by 2 whole raised to the power of m. Now, when we simplify this, this is going to give us 1 plus square root of 5 divided by 2. You can verify that. Minus, we have 1 minus square root of 5 over 2 whole raised to the power of m. And when we simplify this, that's going to give us 1 minus square root of 5 divided by 2. We're almost done. So this is going to be equals to 1 over square root of 5. So this is going to get multiplied to 1 plus, now these two terms are exactly the same, so we can add up the exponents. So we have 1 plus square root of 5 over 2 whole raised to the power of m plus 1 minus, we have 1 minus square root of 5 over 2 whole raised to the power of m plus 1. Fine, we have now finally simplified it, and this is the expression for u of m plus 1. And this is exactly what we needed to show. So this is u of m plus 1. Let's check with p of m plus 1, the statement number 3 as well. Yes, we have gone exactly this statement. So this simply tells us that the statement p of m plus 1 is a true statement. This is true with a condition. This is a conditional statement. This is true for provided, we have to write the condition, provided p of m is true. P of m is true. So if p of m is true, then p of m plus 1 becomes true. This tells us, that means by, we can generalize the statement, so by the principle of mathematical induction, so we can say that the original statement p of n, so that is going to be a true statement. This is going to be a true statement for all values of n, for all values of n belonging to the set of natural numbers. So it's going to be true for all values of n, and n must be greater than or equals to 1. Hence proved.